Good morning. Happy Friday. Going to wait for the number of viewers to increase. Craving sushi. Think I'm gonna have some all-you-can-eat sushi for dinner tonight. Oh, the number of viewers is going down. It was at 22. Now it's at 18. Now it's back up at 20. Now it's at 21. You know what? I think I'm just going to start. All right. Hello, everyone. Hope you're doing well. Mr. Pettibone here. We are going to continue our kinematics. We're almost done with kinematics here. So we're going to talk about projectile motion today. All right. So I'm going to sort of call projectile motion, if I was going to define what is projectile motion, it is sort of like two-dimensional motion under the influence of just gravity. Okay? Under the projectile motion, it's two-dimensional motion under the influence of just gravity. So let me draw kind of a picture that might be something like a projectile motion problem. Okay? So we've got a cliff. Maybe the cliff has a height h, and maybe a projectile is launched off the cliff. Now, because this is two-dimensional, we have to specify what is the launch speed, which I will call v naught, and what is the launch angle, theta. Okay? And then the projectile kind of flies through the air and hits the ground. Okay? So I could ask questions such as, how far does the projectile go? Horizontally. What is delta x? I could ask, how high does the projectile go? What is this distance right here? Delta y. I could ask, what is the time of flight? Things of that nature. These are the types of questions that we want to solve in projectile motion. We are going to be neglecting air resistance. So these calculations are only going to be approximate unless we have no atmosphere. So these calculations would work exceedingly well on the moon. However, they are less accurate on Earth where there's an atmosphere, and they're less accurate. They're even more inaccurate the higher the launch speed is, okay? Because the faster the speed, the more important air resistance is. So if you launch something slowly, air resistance is not really significant. All right. So I'm going to introduce the equations of projectile motion in just a moment, but I want to learn, how do we deal with this initial velocity that is at an angle. Okay, so I want to teach you how to dealing with two-dimensional velocities. Dealing with two-dimensional velocities. So suppose we have an initial launch speed of v0, okay, and the projectile is launched at an angle of theta. Well, when you launch something, at an angle, part of the motion is up and down, and part of the motion is side to side. Okay, so the amount of the motion that is up and down, the amount of the velocity that is up and down is called v y naught. So that's the y component, also known as the y component of the velocity. The horizontal leg of this triangle is called Vx naught, and it is the x component, or the horizontal component of the velocity. Okay, and so the rule for getting the component, if I want the y component of the velocity, I'm going to treat this is a right triangle here, and I just calculate the corresponding leg of the triangle. Okay, so if I can think of v naught, the launch speed. So v naught is the launch speed. I can think about that as the hypotenuse of the triangle, and so you use trigonometry to get the other legs of the triangle. Okay, so if I look at the vertical leg of this triangle, well, it is opposite the angle, and the sine function is opposite over hypotenuse. Okay, so what that means is that the y component of the velocity is v naught sine of the launch angle. Okay, because sine is opposite and this leg is opposite the angle. Okay, the x component, well, that would be the horizontal leg of this triangle, which is next to the angle. It's adjacent. The trig function that has adjacent in it is cosine. Okay, so the x component of the velocity is v naught cosine of theta. All right. So let's do a concrete example with actual numbers, just to illustrate how this works. Let's say I launch a projectile at an angle of 65 degrees above the horizontal. Okay, and I launch it with a speed of 90 meters per second. That's the launch speed, 90 meters per second. How much of that launch speed is vertical and how much is horizontal? Well, the amount that is vertical is going to be 90 sine of 65 degrees. So you want to make sure that your calculator is in degree mode. The reason is that I gave you the launch angle in degrees. So if I had given you the launch angle in radians, then that would be a different story. But I gave you the launch angle in degrees, so you got to calculate in degree mode on your calculator. So I'm going to type in 90 sine of 65. My calculator's in degree mode, and I get 81.6. I'm just going to round it to 82 meters per second. Okay. And then the part of the velocity that is horizontal is going to be 90 cosine of 65. Okay, 90 times cosine of 65 is 38 meters per second. So what that means is that if you launch something at 90 meters per second at an angle of 65 degrees above the horizontal, then it's equivalent to moving 82 meters per second upward while simultaneously moving 38 meters per second to the right. Okay? Let's consider some special cases just so you can see what those look like. One special case is to have a horizontal launch. Okay, a horizontal launch. If you have a horizontal launch, zoom in a little more. If you have a horizontal launch, then that means that the projectile is launched with its initial velocity straight across. So go ahead and type in if you know what the angle of launch is if you have a horizontal launch. Okay? Type into the live chat if you know. And put horizontal launch angle equals this, because I'm about to ask you as well, what would it mean to have a vertical launch? Vertical launch would be a V0 that looks like this. So what is that launch angle? Okay. And then the third one is an example of a diagonal launch, where you go perfectly diagonally is your V0. What's the launch angle in that case? So I'll wait a moment for you to type into the live chat. So I want to know, what is the angle of launch in this case, the angle of launch in that case, and the angle of launch in this case. I'll wait a second. While I'm waiting for you guys to type in what you think the answer is, let me go ahead and talk for a second about V0 here. This is just the launch speed and the launch angle. As the projectile travels through the air, see how the angle changes? The angle that the projectile is headed in changes. Okay? So the velocity is changing. Okay? The speed is changing. The angle is changing. This is only the velocity of the projectile at launch. Okay? Looks like no one wants to answer my question, so I will just say the answer myself. If it is a horizontal launch, we would say 0 degrees. Okay? If it is a vertical launch, it's 90 degrees. And a perfectly diagonal launch would have theta equals 45 degrees. Okay? Now, one of the things about a diagonal launch that's at perfectly 45 degrees is that the vertical and the horizontal legs of the triangle are equal. So you have an equal amount. You're going up and down just as much as you're going side to side. Okay? Okay. So let's go ahead and get to the equations of projectile motion. Okay, the equations of projectile motion. So the equations of projectile motion are based on the first kinematics equation. Okay, so there's going to be an equation for delta y, and there's going to be an equation for delta x. Okay, so let me write down the delta y equation first. V y naught t minus 1/2 g t squared. Okay, so a couple of things here. We can see that because the projectile is flying through the air, it's under the influence of gravity. We can see that the acceleration is minus g. Okay? Acceleration equals minus g. So negative 10 meters per second squared. All right? Just like we did yesterday, or last time. What we did last time, though, is we focused only on straight up and down launches. Okay? But now we're handling the case of diagonal launches. The other thing you want to pay attention to is instead of initial velocity, we have the y component of the initial velocity. So it's that v naught sine of theta. Okay. So the vertical displacement is determined by the initial vertical velocity. That makes sense, right? Why would the vertical displacement depend on the initial horizontal velocity? It's like those are in two different directions, so they don't affect each other. The delta x equation is simpler. It's vx naught times time. And that's it. So notice that this is the horizontal component of the initial velocity. Okay? Notice how there is no extra term. There's nothing here. Why is that? That is because gravity pulls vertically. Okay? Gravity pulls vertically. So this t squared term represents the acceleration. And in projectile motion, all of the acceleration is vertical. So you only have the t squared term in the delta y equation because gravity is only pulling up and down. The horizontal equation, delta x, gravity doesn't pull sideways. So there's no t squared term in the delta x equation. It's only in the delta y equation because that's where the direction of the acceleration is happening. Okay? So you have a constant velocity in the x direction, but you have a changing velocity in the y direction because gravity is pulling vertically. So make sure you have those written down. Okay? So we're going to use these equations. We're going to do 3 examples. So, example. This first example, I will call this horizontal launch off a cliff. Okay? Horizontal launch off a cliff. Okay, so let's suppose you go to the edge of a, let's say, 120 meter tall cliff after being dumped by your significant other. Okay? So you've been dumped, you go to the edge of a cliff, you hurl the mixtape they made for you horizontally off the edge of the cliff. At, let's say, 45 meters per second. How far does it go? Okay, so, you know, do people even make mixtapes for each other anymore? Probably not. Maybe they share like playlists or something like that, but back in my day, you would maybe make a mixtape for someone you like. You say, like, these songs make me think of you. Here, have a mixtape. Okay, so you got dumped and you have this mixtape from your ex-lover or whatever, and you're just like, I gotta get rid of this. You throw it off the cliff. Okay, so here's a picture of what's happening. The cliff, here's the cliff, is 120 meters tall. So that distance right there is 120 meters. Here's you. We're neglecting your own height. You throw the mixtape horizontally at 45 meters per second. So, or meters per second, not degrees. So that means it looks like this. Okay, horizontal launch, angle is 0. Okay, here's the mixtape. All right. Has some cheesy love songs on it. And you throw it off the cliff and it lands here, breaks into a million pieces, just like your heart. And we want to know, how far does it go? Delta X. Okay. So the general strategy with these types of projectile motion problem is, so our strategy is going to be to find the time of flight. Okay, that's the first part. And the second part is calculate the distance traveled in that time. So, I'm going to write the delta y equation and the delta x equation. So the delta y equation is going to be vy naught times time minus 1/2 gt squared. Now, here's the thing. If you have a horizontal launch, then all of the initial velocity is horizontal. None of it is vertical. So this term goes away. All right, this term goes away because it was a horizontal launch. This term, g is 10, 1/2 g would be 5, -5. Okay, so our delta y is really simple. It's just -5 t squared. Again, because it's a horizontal launch, there is no vy naught term. Okay? Our delta x equation is vx naught times time. Vx naught times time. Because it was a horizontal launch, all of that launch speed went horizontally. Okay? So Vx naught is actually going to be the full launch speed in this case. So it's going to be 45 t, because all of the launch speed was horizontal. Okay, so how do we proceed? Well, I'm going to call this the starting point, and I'm going to call this the ending point. So we can see the difference in elevation between the starting point and the ending point is 120 meters. So this means, and it goes, the mixtape goes down 120 meters. So we have, for this problem, that delta y is -120 meters. Okay? So we can plug that in. So delta y is -120. All right? So -120 equals -5t squared. So I can take that and I can solve for time. So that means time is going to be, well, 120 divided by 5 is 24. So I get t squared equals 24. and then I take the square root of both sides, and it's going to be about 4.9. Square root of 24 is 4.9. So the time of flight is 4.9 seconds. Okay? Now that I know the time of flight, I can then use that in my delta x equation to figure out how far horizontally it goes. Okay? So my delta x is going to be 45 times 4.9, and that's 220 meters. So the mixtape is going to land 220 meters to the right of where it started. Okay? So that is an example of a projectile motion problem. And I will reiterate that what was I going to reiterate? I don't even remember what I was going to reiterate, so it can't have been that important. Okay. Oh, I think I wanted to say that the general strategy is find the time and then calculate the distance in that amount of time. Okay? Let's do another example. This example I'm going to call diagonal launch across a flat surface. Okay, so this problem does not have a cliff. It has a flat surface. So let me draw it. Here's the flat surface. And this problem is going to be like a military sniper. Okay? So here's a sniper rifle. Here's the sniper. Okay. And the sniper fires the projectile at 500 meters per second at an angle of 10 degrees. Okay? And we want to know, how far does it go? So just like the last problem, we want to figure out how far horizontally does it go. Now, because this is a diagonal launch, we have to do that initial velocity triangle. Okay? Now, by the way, just because the launch speed is 500 meters per second doesn't mean that it's always going to be going 500 meters per second. That's just the initial speed. This is just the initial angle. These quantities change as the projectile is curved by gravity. Okay? So I have my initial velocity triangle. 500 meters per second is the hypotenuse, and this angle is 10 degrees. So to get the initial vertical velocity, I would do 500 sine of 10 degrees, which is about 87 meters per second. Okay? The initial horizontal velocity is 500 cosine of 10. And that is 492 meters per second. Okay? So because we have a diagonal launch, we want to just go ahead and figure out what are the legs of the initial velocity triangle. Then we go to our delta x equation and our delta y equation. Okay? Our delta y equation is v y naught t minus 1/2 gt squared. V y naught is 87. So I have 87 t minus 1/2 gt squared, so minus 5t squared. So that's our delta y equation. Our delta x equation is vx naught times time. Vx naught is this 492, so I have 492 t. All right? So these are our two equations of projectile motion. All right? So what we need some other condition, okay, to solve this problem. There are too many variables as it is. So I'm going to consider the moment of launch to be the initial time, and the moment that the projectile lands to be the final time, okay? And so the projectile is launched across a flat surface, so that means that the place that it's launched from and the place that it lands have the same elevation. That was not the case in this problem because the mixtape is drops a certain distance. But in this problem, it goes up and it goes down to the same elevation. So it's a lot like the chicken wing problem in that sense. So I have that delta y equals 0 for this problem, okay? Because it's going across a flat surface. So I can set 0 equals 87t minus 5t squared. Add 5t squared to both sides. Okay. Divide both sides by 5. That's going to give 17.4. And then divide both sides by t. And we get that the time of flight is 17.4 seconds. Okay. Let me just double check my arithmetic there. Yeah. Okay. So now, if I want to know how far does it go in that time, I then take this number and I plug it in for time right here. Okay. So delta x is 492 times 17.4. And I get 8,561 meters is the horizontal distance. Okay? So that would be the answer to that problem. Again, this is somewhat unrealistic because bullets are traveling really fast, 500 meters per second. That's greater than the speed of sound. So they're going to experience a lot of air resistance. Okay. So it's going to be quite a bit less than that in reality, but this is just a first approximation. Okay. If you take my AP Physics C class, we learn more about how to deal with the effects of air resistance. Okay, we'll do one more example and then switch to the Zoom room. So the last example is in the previous example, how far does the projectile, or how high does the projectile go? How high does the bullet go above its starting point? So basically what I'm asking for is what is that distance right there? Okay? So here's the key to this problem. Okay? The projectile is launched at time 0, and we know that throughout its entire arc, it hits the ground 17.4 seconds later. This is a symmetrical arc, theoretically. So at what time does it reach the highest point? Go ahead and type it into the live chat if you know the answer. At what time does the projectile reach its highest point? If the entire arc is 17.4 seconds. Yeah, exactly, 8.7 seconds, so halfway. Because it's a symmetrical arc, halfway is when it reaches the highest point. So it reaches the highest point at 8.7 seconds into the journey. Okay? So the key is that the highest point is reached halfway through the motion. Okay? The highest point is reached halfway through the motion. So what I'm going to do is I'm going to take my delta y equation, which is 87t minus 5t squared, and I'm going to reuse it. So in the last one, we set delta y equals 0, but now obviously delta y is not equal to 0, okay? Because it's the highest point. The projectile does go up in the air along its trajectory. Oops, I forgot a t there. Instead, what I'm going to do is I'm going to plug in t equals 8.7 seconds. So I have delta y equals 87 times 8.7 minus 5 times 8.7 squared. Okay? So I have 87 times 8.7 minus 5 times 8.7 squared. And I get that this projectile goes 378 meters into the air. So that is the maximum height that the projectile achieves. All right? One of the things here I want to talk about just really briefly before we go over the Zoom room is you really need to be careful about saying that the highest point is reached halfway in the motion, okay? Because the highest point being reached halfway was dependent on the fact that the projectile is launched across a flat surface, and so it goes in this symmetrical arc that is the same. You can flip it this way and it's the same. If we have a problem that is not symmetrical, like this horizontal launch off a cliff, for this problem, the highest point is going to be 120 meters, right? Because immediately after it's launched, it starts to drop. Okay, it wasn't given any upward velocity to start with, so it just immediately drops. So here, if I wanted to know what time does the highest point occur, it's at 0 seconds at the moment of launch, not half of 4.9 seconds. So you got to be careful. The highest point is reached halfway only if you have this kind of symmetrical situation. Okay, so that's the end of my lesson. I will see you in the Zoom room.